Okay, right. So Alhamdulillah, we have arrived to our final lecture. Okay, for this semester. Right. So hopefully, hope you can view the slides clearly. Yeah. All right. So this will be our last lecture for this semester, which will be the part 2 of lecture 11. Basically, this is a continuation from the topics that we have learned last week, okay, on the optical system design. So if we can recall back the things that we have learned last week, we have learned about the optical system design, specifically on the topics of power budget, yeah, power budget analysis, and how we are designing the optical system based on the gain, yeah, based on the gain, based on the loss induced by the fiber optic itself, and also based on the sensitivity of the receiver. So these are the things that I have learned last week, yeah. So hopefully you have understood these topics clearly on the power budget analysis. So for today, we're going to continue our system design analysis, but for this case, the emphasis will be on the rise time budget. Okay, the rise time budget, or we also call it as a bandwidth budget. Yeah. Okay, so that should be our main topics for today's lecture. So this will be the content of our lectures today, which is on the rise time budget. Okay, and this is the CI. Yeah, from the CI is very simple. Yeah, just mentioned about the optical system design using two methods, whether we have a power budget or the rise time budget analysis. Okay. Right. So the rise time concept, I think we have come across. Yeah, we have come across these topics of rise time in chapter 5. Yeah, if we can recall in chapter 5 when we learned about the photo detectors. Yeah, we have learned about the rise time. Yeah, the rise time. Basically, the rise time is very important, in which it will enable us to calculate. Yeah, what should be the bandwidth of our component. Yeah, bandwidth of component. So in this particular case, in chapter 5, when we learn about the rise time, basically the rise time is used to measure or calculate the bandwidth of our receivers or photodetectors. Okay. So this is the diagram that I just cut from the chapter 5 lectures or slides. Yeah, what is meant by the rise time? So rise time is basically a time value between 10% and 90% of the voltage output value or the voltage value. Yeah, so between 10%, 90%. So this will be the rise time. Yeah, the time between the 10% and 90% of the voltage value. So allow me to go back to the Google Meet, yeah, because the students want to enter the class. Okay. Right. So let us proceed. Sorry for the interruption. Yeah. Okay then. So as I mentioned before, time needed. So what is rise time? So rise time basically is the time needed for the photodiode, yeah, for the photodiode to respond to optical input and produce the external current. So this is what we call as the rise time. Okay, and the rise time basically is depending on the photodiode capacitance, yeah, which is the C, yeah, sorry. Okay, this is C, okay, the CD, okay, and then we have the load resistance, which is the RL, yeah, the RL, and design of photodiode. So this is based on the design of the photodiode itself, whether it's a PD, PIN, or the APD design. Yeah, so we're not going to touch on that design, but we understand now that in terms of the components, yeah, components that the rise time will be basically depending on the capacitance value and also on the resistance value. So we're going to see this further in the next slide later on. Yeah. Okay, so as mentioned before, the rise time is measured between 10% and 90% of the amplitude. Okay. Right. So this is basically it's a concept of rise time. So I believe that you can understand this because we have touched this a bit, in our lectures in chapter 5. Yeah. Okay, so now we're going to see how the rise time and the bandwidth is actually related. Okay, because this is very important, because later on we're going to formulate an equation which will be useful in calculating the bandwidth, bandwidth of the components and subsequently bandwidth of the system. Yeah. Okay. So as mentioned here that the system rise time, okay, it can be used to determine the possible limitation of the optical system bandwidth. Okay, so the words here is possible limitation, yeah, because we know that for the optical system, the bandwidth is very important, yeah, it's very important, but this bandwidth will be limited, yeah, will be limited by this rise time value. So that's why we have this topic is on the rise time budget or the bandwidth budget, yeah, because if we can configure the rise time value, so we can modify, or we can obtain, or we can calculate what should be the offered bandwidth, yeah, for the given component used in our optical system. So basically, what we're going to learn today is much related to the assignment that I gave to you last few weeks. Okay, so basically the assignment that I gave you can be solved if you understand the topics of budget and the topics of bandwidth budget clearly, yeah. So these two lectures, 11 part 1 and 11 part 2, will be very important for you to solve your assignment questions, yeah. Okay, let us proceed then. So basically the maximum system bit rate, yeah. So this is the bit rate. Okay, bit rate, BT, is defined in terms of the total optical system rise time. Okay, so we can find the bit rate with the TCs, which is the system rise time in total. So the BT and the TCs, we're going to find out what should be the relationship between the two later on. Yeah, the bit rate of the system and the system rise time. Okay, right. So this is what we have learned in chapter 6. Yeah, so this is the process. Yeah, this is the flow of getting the relationship between the bit rate and also the system rise time. Okay, so we start with this equation of the receiver bandwidth, which is 1/2 pi RC. So we have seen this equation in chapter 6. Yeah. Sorry, students want to get in the class. Allow me to go back to the Google Meet. Yeah. Sorry for this interruption. Okay, go back this slide there. Okay, so this is basically the equation that enables us to find the bandwidth. Okay, so this we have seen this equation in chapter 6 last time. Yeah. So how can these equations being formulated? Yeah. Okay, so basically this is related to this circuit. Yeah, if you can recall back when we learned about the optical receiver circuits, we have the capacitance, we have the resistance, the resistance, the capacitance of the circuit of the receiver circuit. So basically, this can be related to what we have learned in year 2 or second year of our program. If we can go back to second year of the program, we have learned about the signal line system, signal system in semester 1, second year. So if we can recall that we have the low pass filter, the low pass filter, in which the low pass filter basically can be produced either by using the RC component of the circuit, or we can have the RL component of the circuit. This is first order circuit, first order circuit, whether it's RC or RL. So in this particular case, we're using the RC circuit, and for the sake of, for the RC circuit of the low pass filter, the output voltage is measured across the capacitor, measured across the capacitor. And if you can recall back, when we have this circuit for the low pass filter, you are going to get that the cutoff frequencies, the omega C, the cutoff frequencies shall be equals to 1/RL. Okay, so if we can have a look at this particular low pass filter frequency response, okay, so this is your frequency F, That's your amplitude of your frequency transfer function. Okay, sorry, yeah, this is what we have done in second year. So I just want for you to relate the things that we have learned last time with these topics here. Yeah. So this will be your RC. So 1 over RC. Yeah, 1 over RC. And that should be your 3 dB or negative 3 dB. Okay, where we have this is what we call as the cutoff frequencies. Yeah. So if I can have that should be your omega c, or it can be equals to 1 over RC. And we have then FC should be equals to 1 over 2 pi RC. Yeah. So that basically this is your bandwidth. Yeah. That's your bandwidth. Yeah. Bandwidth of the system is a 3 dB bandwidth. That's why we have the bandwidth is equals to 1 over 2 pi RC. That's the reason why we have the bandwidth of 1 over 2 pi RC. Yeah. Okay. So for this particular case, we assume that in our system, yeah, our optical system, that will be the input pulse from your fiber optic. Sorry, student trying to get in the class. Yeah. Sorry for this interruption again. Sorry for that. Okay, so assume that this is the input pulse along your fiber optic structure. Okay, so we have this your fiber optic structure. So basically, this is your impulse that is said to propagate inside your fiber optic structure. Okay, and then we have the receiver at the end of your system. Okay, so when this particular input pulse, which is in time domain, pass through your receiver circuit, in which you're going to get the output voltage here, yeah, up the voltage here. So basically, you can relate, yeah, we know that since the bandwidth of your optical receivers is 1 over 2 pi RC, okay, in which the cutoff frequencies is omega c is equals to 1 over RC, okay, we can have the case whereby the output pulse, yeah, the output pulse for your, there's a chat, sorry. Okay. Okay, I'll get back to this. Yeah, okay. So basically, this is your input pulse. Sorry for this interruption. Okay, so this is your input pulse, which is fit to propagate along the fiber optics. Yeah. Okay, so we have the input pulse propagating inside the fiber optics, and that should be your receiver circuit, which consists of the RMC component. And knowing that the RC component, I mean the receiver circuit, the cutoff frequency of it is equals to 1 over 2 pi, sorry, 1 over RC. Okay, 1 over RC, or you can say that the frequency is 1 over 2 pi RC, which is the bandwidth of the system. Okay, we can say that when this particular input pulse passing through the circuit, so at the output of these receivers, or at this point measured along across the capacitor terminal, we can see that the voltage output will be measured to be look like this. Okay, in which the output voltage, yeah, initially we have a very nice square wave function or rectangular function. So passing through this circuit of receiver with the cutoff frequencies of 1 over 2 pi RC, so the output voltage, which is measured across the capacitor, will be having this value. The V out will be equals to the V, which is the input voltage, yeah, 1 minus exponential negative T over RC, where the 1 over RC is the cutoff frequency. So I'm not going to explain this in detail, yeah, because the mathematics of it will be quite some time to prove, yeah, but we understand that from this relationship between the input pulse, which is nicely formed in terms of the input pulse, yeah, rectangular function, passing through the receiver circuit. So at the output pulse, we're going to have this equation of the output voltage, yeah, measured across the capacitor. So from this particular output pulse form or waveform in time domain, yeah, so we can measure the rise time of it, yeah, rise time of it, of the output voltage, because we want to find out what should be the relationship between the rise time and the bandwidth. Okay, so we have learned that the rise time is the time measured or calculated between the 10% of the amplitude and 90% of the amplitude. Okay, so that should be basically the rise time. Yeah, if I can sketch this. Okay, basically that should be your rise time. Yeah, we have this as your tau r lah. So tau r stands for the rise time value. Yeah, between 10% and 90% of the amplitude. Okay, so in order for us to calculate this tau r, what we have to do is that we have to substitute the value of V out, yeah, in this equation, yeah, the value of V out to be equal to 0.1 V and 0.9 V. So that basically we're going to have two equations there, okay, in which this should be 0.1 V because your full voltage is V, yeah, and for this voltage it should be 0.9 V, 10% and 90%, yeah. Okay, so basically if we substituted this information, yeah, the V out as 0.1 V and 0.9 V, we are supposed to get two equations then, yeah, two equations with different time value, yeah. For example, if we have V out of 0.1 V, you can substitute that the T, yeah, this value of T shall be written as a T1. And when we have the V out as 0.9 V, you are going to have your output, the time shall be equals to T2. So the rush time basically should be a difference between the T2 and T1. So T2 minus T1 will give us the tau R, and end up you're going to have this relationship. You can prove this on your own, that the rise time value is basically equals to 2.2 of RC, in which we can see a relationship between the rise time and part of the component of bandwidth, right? Because we have seen just now that the bandwidth is 1 over 2 pi RC. And from this relationship of the graph, we can see that the rise time is returned to be 2.2 of RC. So now we can see relationship between the rise time and the bandwidth. Okay, so we're going to proceed now. We're going to use both equations 1 and 2, and this is the case. So we're combining now the equation 1 and 2, and end up we're going to have the rise time for the receiver circuit. By combining 1 and 2 just now, the rise time will be equal to 0.35 divided by B. So this is the equation that relates the rise time and also the bandwidth, yeah? So rise time, tau R, equals to 0.35 divided by the bandwidth of B, which is always written to be in gigahertz value, yeah? All right then. Okay, so we can use this idea in our optical system. So in our optical fiber system, the rise time, normally we use a thesis, yeah, as a representation of a system rise time in optical fiber. So the system rise time, which is equal to this, yeah, will be written as 0.35 divided by B. Okay, yeah, so that should be the equation that relates the system rise time and also the bandwidth of our system. Okay, so now for our digital case, yeah, because we are using the fiber optics, yeah, and for the modulation, for the line coding, yeah, for line coding, in order for us to send a bit 1010 inside our fiber optic structure, normally we need to use the what we call this the on-off king, yeah, the on-off king. So on-off king can be divided two types, where we have the NRZ, okay, and also RZ, yeah. So this is two common method of modulation for the line coding, yeah. So for the NRZ, we can write that the bit rate, yeah, the bit rate for the NRZ system shall be equals to 2 times the bandwidth, okay, 2 times the bandwidth. Whereas for the return to zero, the bit rate shall be equals to the bandwidth itself, yeah. Okay, so this is the diagram that shows the difference between the NRZ and RZ. I believe that you have learned this in detail in PCOM, yeah, in third year first semester, I believe. Okay, so for the NRZ, every bit is represented by one symbol. Yeah, let's say 1, we have equals to 1 symbol, 0 be 1 symbol, and so on. But for the LZ, bit 1 is represented by combination of signaling 1 and 0, okay, in which the every bit do have a return to zero signaling. Yeah, so that's the difference between the NRZ and the RZ. So basically, based on this, we can see that the bandwidth for the RZ will be 2 times as compared to the bandwidth for the NRZ. So that's why we have the equation that the bit rate for the NRZ is 2B, while the bit rate for the RZ is equals to B. And as such, when we substitute the equation here, where B is now substituted based on the equations here, for the case of NRZ, we can see that the thesis will be equals to 0.35 divided by B, which is BT, the bit rate divided by 2, and end up going to have that the rise time for the case of NRZ line coding will be 0.7 divided by BT, or 0.7 divided by bit rate. Whereas for the RZ return to zero line coding, when we substitute the B as equals to BT in this equation, we're going to have that the rise time of the system, if you're using the RZ line coding, should be equal to 0.35 divided by the BT. Yeah. So this is the equation that relates the rise time and also the bit rate or the bandwidth of our optical fiber system, and this will be very useful when we want to design our optical system using the bandwidth budget or the rise time budget analysis. Yeah. All right then. Okay. Let us proceed then. So what is meant by rise time budget analysis? So what we have learned just now, we have come up with the equation that relates the rise time and also the bit rate or the bandwidth. So for this particular case, we're going to see what are the components in our optical fiber system that contribute to the rise time value, or the total rise time value of our optical system. Okay, so that should be given by this slide then. So we have the equation, the first sentence here is that the optical system rise time will be determined or may be determined from the rise time of individual system component, Okay, so we have a components in general. We have the transmitter, you have the fiber cable itself, and we have the detector. Okay, for the fiber cable, there are a few components that will be very useful or will be contributing to the rise time. So we have learned in chapter 4 that the fiber cable, in case if I have the multi-mode fiber, okay, so basically the dispersion will be the factors that affect the rise time of our system. So we have, for the case of MMF, the rise time of this fiber cable will be contributed by the intermodal dispersion, intermodal dispersion, and also will be contributed by the material dispersion, material dispersion. Okay, so these are the contributors for our rise time in the fiber cable itself. And also another one, we have what we call that the waveguide dispersion, waveguide dispersion, but normally waveguide dispersion will be very much effect as compared to the material dispersion. So the same things happen for the SMF, whereas for the SMF, we only have the effect of material dispersion and also the waveguide dispersion. There should be no effect of intermodal dispersion. So I believe that these are the things that we have clearly understood from what we have learned in chapter 4 last time. Okay, so back to the discussion of rise time budget. So basically, the rise time of the system in total can be written as this equation here, by this equation here, where the total system rise time for the optical fiber-based system will be square root of summation of Ti squared from 1 to n, where n is the number of components in our system, okay, and Ti here is the rise time of the individual component. Ti is the rise time of the individual component. So basically, if we base on this first case here, if we have transmitter, fiber cable, and detector, so basically, in general, we are going to have 3 components: the transmitter rise time, the fiber cable rise time, and the detector rise time. So that will contribute to our total rise time of the optical system. So that should be the equation that can be used in general. The T system and the total rise time of the fiber optic system will be Ts squared TS stands for the rise time of the light source, plus TF squared. So TF is the rise time of the fiber cable, which include the dispersion effect of our fibers, as I mentioned before. We have the TD squared. TD is the rise time of the detector, and TA squared is the rise time of the amplifier in case if we are using the amplifier in our system. So that should be the equation that enable us to find the rise time of the system. Okay, some books, they use a total rise time by this equation and multiply with 1.1. 1.1. But from my readings, most of the books, they just have this equation in which they ignore the effect of 1.1 there. Okay, so for this particular case, the total rise time, I will just use this equation without the 1.1 constant. So we agree that for the rise time value, for the total rise time of the optical system, we are going to calculate it based on this equation, which is the square root of the rise time for each component square. Yeah, okay, right. So this will be the equation that will be used in calculating the rise time of our optical system. And from this rise time, if we manage to get the total rise time of our component, subsequently we're going to get the total rise time here, and from this we can then use it to calculate the bandwidth or the bit rate. Yeah, because from the equation that we have seen just now, if you are using the NRZ, the thesis relationship between the total rise time and the bit rate is 0.7 divided by the bit rate. Whereas for the RZ, the total rise time should be given by 0.35 divided by the bit rate. So we're going to see that by knowing the total rise time value, okay, we can then roughly estimate the maximum system bit rate or the bandwidth of our optical system. So that's the basic ideas of how we can use the rise time budget or the bandwidth budget in our optical system. So basically, it's more towards designing what should be whether the system that we design, whether it fulfill the bandwidth requirement of our system. So that should be the main purpose of the rise time budget or the bandwidth budget analysis. Okay, so by calculating the total rise time, by calculating this equation here, we can use it to design or to know whether our system that we design, whether it is compatible, or whether the bandwidth that we are designing, is it enough to cover our application. So that is the things that we have understand from this slide. Okay then. Is there any questions then? No, Okay, let us have a look at this example just to ensure that you really understand on the rise time or the bandwidth budget analysis. Okay, so for this example, we are given a case whereby an optical fiber system is to be designed to operate over, so this is 8 kilometer, this is 8 kilometer length without repeaters. So the rise times of the chosen components are, okay, so we are given now that the LED is having a rise time of 8 nanosecond, which is the TS is 8 nanosecond. The fiber, we have two dispersions there, which is intermodal and intramodal, and we believe that this is basically a multimode fiber. Okay, so we have the relationship here that we have two components of rise time. So the rise time for the fiber consists of two components there, dispersion of intermodal and intramodal dispersion. And then for detector, we have the rise time of the pin photodiode is 6 nanosecond. Okay, so with the given system rise time or with the given rise time for the components, you have to estimate what should be the maximum bit rate that may be achieved on the link using the NRZ or the RZ format. Okay, so you have to calculate the total rise time, based on the given rise times of the component. And subsequently, you need to estimate what should be the maximum bit rate that can be offered, that can be offered by this particular system, using the NRZ and the RZ format. Okay, so let us proceed with the calculation of the total rise time. So from what we have done before from the previous slide, the total rise time, the thesis, shall be equals to square root of combination of 8 nanoseconds, okay, 8 nanoseconds squared, which is the total rise time of the LED, okay, plus the rise time due to the dispersion. So we have two dispersions there. For the molar dispersion or intermolar dispersion, we have 5 nanoseconds need to be multiplied with the length, yeah, because we have 8 kilometer length, and this is the rise time per kilometer. So it should be 5 nano times 8 kilometers square. So we have the second effect of dispersion. This from the intramodal. So we have 1 nanosecond multiplied with 8 kilometers square, plus the rise time of the detector, which is 6 nanoseconds. So we have 6 nano squared. So that should be the rise time of the components. So calculating this, we are supposed to get the total rise time for the systems here shall be equals to 42 nanoseconds. So you can calculate this on your own, yeah? So we're going to get this total rise time for our system. So from this total rise time, we can subsequently use it to calculate the bit rate. So if you're using the NRZ line encoding, okay, so your bit rate shall be based on the equation of 0.7 divided by the total rise time. And when we calculate this, it should be 0.7 divided by 42 nanoseconds. And by calculating this, you're going to get the bit rate shall be 16.6 megabit per second. Yeah, so that should be your bit rate. Whereas if you're using the RZ line encoding, so your bit rate for this will be 0.35 divided by the system rise time, and by calculating this, we're going to get that the bit rate for this will be 8.3 megabit per second. Okay, so NRZ will be having higher bit rate as compared to the RZ component. Yeah, right then. Okay, yeah. So hopefully you understand these questions, the example here. So basically from the equation, from the calculation of the system bit rate in total, we'll be able to calculate what should be the maximum bit rate that can be offered if you're using the NRZ line coding or the RZ line coding format. Yeah. Okay, then let's have a look at these examples then, the second examples here. So for this example, we are given NRZ line coding. Okay, we are given the NRZ line coding of a 20 megabit per second. Okay, so that should be your NRZ line coding. The bit rate of it is 20 megabit per second. Optical system with a 6 kilometer length. Okay, and we are given the following rise time for the component of the system. Okay, we are having the rise time for the LED is 15 nanoseconds. The rise time, the spectral width is 40 nanometer. Okay, that's spectral width for the LED. Okay, we are given further that the fiber optic dispersion parameters is DM. Yeah, I believe that you can still recall the DM. Yeah, that we have learned in chapter 3 before. So chapter 4 before. The DM is 87.5 picosecond per nanometer per kilometer. And the pin PD, the pin photodiode receiver rise time is 40 nanoseconds. Okay, so these are the rise time for the components that is proposed to be used in our systems here. Okay, so the question is, show that the components that we have that have been selected, that have been proposed in this system design meet the system design criteria. Yeah. Okay. So before we can proceed, basically we need to calculate. Yeah, we need to calculate what should be your total rise time. Yeah, what should be the total rise time, which should be equals to square root of the rise time of your source plus rise time of your fiber optics plus rise time of your detector. Okay, so this is the equation that shall be used to calculate the total rise time of the system. But first thing first, you need to know that from the first, for the quest itself, it stated here that we are using the NRZ line coding with a given data rate of 20 megabit per second. So basically, from this information, we can calculate what should be the system rise time. Yeah, what should be the system rise time? Yeah, because we have learned previously that when using the NRZ line encoding, the system rise time is calculated based on 0.7 divided by the BT or the bit rate. So since we know that the bit rate used in this particular case is, the bit rate that we are proposed, that we propose in this particular case is 20 megabit per second. So your total rise time should be 0.7 divided by 20 times 10 power of 6. And basically, when we calculate this, it should be equals to 35 nanosecond. Okay, so this is the total rise time that is calculated based on the proposed 20 megabit per second bit rate of the optical system, in which this 35 nanosecond is said to be the maximum, the maximum allowable rise time degradation. Okay, which means that the rise time that you're going to calculate, based on these components rise time value, it cannot exceed this value of 35 nanoseconds. Because from this relationship, we have the BT equals to 0.7 divided by T6. Okay, so you need to ensure that the T6 that you are calculated here shall be smaller than 35 nanoseconds, because if the calculated rise time is bigger than this, you're going to get the bit rate which is smaller than 20 megabit per second. Am I right? I repeat again. If your calculated rise time is bigger than 35 nanoseconds, if we substitute in these equations, you're going to get that the value of rise time, which is bigger than 35 nanoseconds, will result on smaller bit rate, which is unwanted, right? So you need to ensure that your calculated rise time shall be smaller than 35 nanoseconds. That is why I did mention here that by calculating the rise time based on the given bit rate, the value of 35 nanoseconds here is defined to be the maximum allowable rise time value. So we need to calculate this rise time. If the total rise time calculated based on the equation here is smaller than 35 nanoseconds, so we can say that the component proposed in the design do meet the system design criteria. Okay, so let's calculate now. So we have TS is 50 nano squared plus fiber optics here. Sorry, I did reinstall the driver, but the problem persists. I'm not sure why. Okay, never mind. So we add this with the fiber optics rise time. Okay, so for the fiber optic rise time, we need to be based on this. And from what we have learned in chapter 4, we can calculate the dispersion, the material dispersion, by using the equation of delta M shall be equals to the dm, which is the dispersion parameters, multiply with the length, multiply with the spectral width of delta lambda. So we're going to get this as 87.5 picosecond, okay, multiply with a L, which is 6 kilometers, and multiply with the spectral width, delta lambda, which is 40 nanometer. And by calculating this, you're going to get that your dispersion parameter, the material dispersion value will be then equals to 87.5, correct, times 6 kilometers times 40. Okay, so that should be substituted into these equations here. So so we're going to have a delta M squared straight away. We just substitute into this, so it's understood. So the value that we're going to get here from this calculation will be substituted here as representation of your fiber rise time. okay, plus the TD, which is dispersion of your rise time of your photodiode or receivers, which will be 14 nano squared. Okay, so by calculating this, you're going to get that the total rise time for this will be equal to 29 nanosecond, which is smaller than the 30 nanosecond. So we can see that based on this calculation, which shows that the calculated rise time is smaller than the maximum allowable rise time, we can see that the components that have been proposed in this design can meet the system design criteria. Okay, so that should be the answer for this example. Okay, any question for this example? Hopefully by this example, you can now understand how to design the optical system by using the second method, which is the bandwidth budget or the rise time budget analysis. Yeah. Okay, then let us proceed with the next example here. So in this example, we are given an optical system with the following specification. Yeah, we have the laser use is lambda, wavelength is 1.55. The spectral width, the delta lambda is 0.5 nanometer. The power transmit is 5 dBm. Yeah, 5 dBm, and the rise time of the laser or laser source is 1 nanosecond. Okay, for detector, the detector rise time is 0.5 nanosecond. The sensitivity is -40 dBm. Yeah, sensitivity is the smallest. Yeah, smallest power that can be recovered. Yeah, that can be recovered by the detector. While the preamplifier is 1.3 nanoseconds, the rise time of it. Dispersion of the fiber is 15.5 picoseconds per nanometer per kilometer. This is the molar dispersion of the fiber. The length is 100 kilometers, while the attenuation is 0.25 dB per kilometer. The coupling loss is 3 dB. The connector loss is 2 dB. We have two connectors there. Connector loss is 2 dB in total. While the splice loss, we have 50 splices. Total loss due to the splices is 5 dB. And it's given that the system use is 400 megabit per second. That should be the data rate proposed. While the coding is NRZ with the length of 100 kilometers. Yeah. Okay, so the question is, show by suitable methods that the choice of components are suitable for the link. Okay, so if you base on these given examples, you notice that we are given both conditions, yeah, both informations. We are given the power transmit, yeah, the power transmit, the receive power, the attenuation of the fiber, the connector loss, the splices loss, and the source coupling loss together with the rise time value for the components. So if you base on this information, since we are given both sides, yeah, we are given both sides, that will be very useful in power budget and the rise time budget analysis. So basically, the method that shall be used here in calculating or in showing whether the components used are suitable, we have to adopt two techniques then, which are the power budget. Yeah, have to use the power budget, and also we need to use the rise time budget. So we have to adopt these two methods to calculate the to show whether the methods used, the component used are suitable for the link. Yeah. All right. So let's have a look at the solutions for this example. Okay, so let us proceed now with the rise time budget first. Yeah, so we proceed with the rise time budget. Okay, with the rise time budget. Right. So from the rise time budget, if you can recall back, we have the total rise time shall be equals to square root of the T source plus the rise time of the fiber optics or dispersion fiber optics plus the rise times of your receivers, yeah, detectors. Okay, so let me see, yeah, let me go back to the previous one. Okay, so this is the case, right? So for the dispersion, we have only dispersion of 15.5 picosecond per nanometer per kilometer. Okay, so that should be useful then. Right, so from here, when we calculate the rise time, okay, I forgot that we have the amplifier, yeah? amplifier, which is 1.3 nanoseconds. So we need to add that together. So we have the contribution of rise time for the amplifier, which is TA squared. Okay, so when we calculate this, we're going to have a square root of TS, which is the source, which is 1 nanosecond, so 1 nano squared, plus the detector. Sorry, the fiber optic itself is, fiber optic is 15.5 times the length of 100 kilometers times the spectral width of 0.5 picoseconds. Okay, let's go back to this. 0.15 nanometer, sorry, 0.15 nanometer. I apologize, yeah, sorry, that should be nanometer, yeah, in nanometer range, sorry for that. Let me check that. So 15.5, okay, we have 15.5, which is the dm, length is 100, and the delta lambda is 0.5 nanometer. So we have 15.5, 100, and 0.5 nanometer. That should be the dispersion value squared. Okay, plus the rise time of the detector, which is 0.5 nanoseconds. Okay, 0.5 nanoseconds. And for the amplifier is 1.3, so we're going to use that. So we're going to have 0.5 nano squared plus 1.3 nano squared. So that should be the total rise time calculated, yeah, based on the components. So end up going to have the values for these. When we calculate further, going to have the value will be 1.73 nanosecond, yeah. So that should be the total rise time of your components. So we're going to see whether does it meet the system design criteria. So how to ensure that these meet, yeah, the system design criteria. So what we have to do is that, so we are given basically that your system will be based on these NRZ and the bit rate of 400 megabit per second. So from these, you can calculate what should be the rise time value, yeah, that we're going to get, yeah. So we're going to have 0.7 divided by the 400 megabit per second. So that basically will give us the value of 1.75 nanoseconds, yeah. So basically, this should be the maximum, yeah, the maximum rise time that is allowable, yeah, that's allowable. So if we compare the calculated rise time and the maximum rise time, we can see that the calculated rise time 1.73 nanoseconds is smaller than the maximum allowable rise time. So when this happens, we can see that the system component that we propose here meet the criteria. Yeah, so which means that the bit rate or the bandwidth can be covered, yeah, can be covered by these particular components of the system. Okay, so that should be the first method, which is based on the rise time budget. So let us proceed with the power budget method or power budget analysis. So I'm going to erase this first. Okay. Okay, so now I'm going to use the power budget. Yeah, power budget. Right, so the second method is based on the power budget method. Okay, so for the power budget, if you base on what we have learned in the previous lectures, yeah, last week lectures, if we can recall back, the power transmit, the PTX, will be equals to the power receive, okay, plus the channel loss, okay, and if possible, we are going to have the system margin, yeah, system margin. Okay, so basically, if we can base on the previous slide here, we have that for the laser is 5 dBm, which is the PTX, yeah, is 5 dBm. The PRX, which is the receiver sensitivity, is negative 40 dBm. The fiber is 0.25 dB per kilometer attenuation. The connector loss is 2 dB. The source coupling loss is 3 dB, and the splice loss is 5 dB. And the length is 500 kilometers. So we're going to use this all together. So basically from here, we're going to have that the the power transmit will be 5 dBm. Okay, I bring the receive power to the left hand side. Yeah, so minus the receive power will be negative 40 dBm, which is the sensitivity. And for the channel loss, it consists of few components. The first one is due to the attenuation. So we have 0.25 dB per kilometer. Yeah, multiply with the length, which is 100 kilometer. Okay, so this is 0.25 dB per kilometer, yeah, times 100 kilometer. So you're going to have a dB value in dB, plus the loss due to the coupling, which is 3 dB, plus the loss due to the connectors, which is 2 dB, plus loss due to the splices, which is 5 dB, and end up we are going to get the power margin, yeah, system margin, system margin. So let us proceed now. Okay, so when we proceed further, the left hand side, we're going to have the value of 45 dB. Okay, the range, yeah, the difference between these two is in dB, so 45 dB. Whereas for the right hand side, we're going to get the value of 25 plus 28, 30. Yes, let me see. 25 plus 3 will be 28. 28 plus 2, 30, 35. That's be 35 dB plus the system margin. So end up going to have the system margin equals to 10 dB. So from here, as we have learned last week, that for the system to work properly, the system margin must be a positive value. Yeah, must be a positive value. So based on this, when we calculate this based on the equations here, we have obtained that the system margin is positive 10 dB. So which means that the systems, the components that used in the systems can ensure that we are going to get, I mean, the system can work properly. Yeah, the system can work properly. So that should be the conclusion from the calculation of the power budget, which produce a positive system margin, and the calculation of the rise time, which produce a value which is smaller than the maximum allowable rise time. So based on this, we can see that the system, the component that have been proposed in this system design can ensure the functionalities of the system. Yeah. Right then, is there any question for this example so far?
No, Doctor.
Oh, yeah. Okay, so let us proceed with the examples again. Okay, so for this examples, we are given a NRZ coding. Okay, NRZ line format used to connect 2 points of 10 kilometer apart and designed using a 30 megabit per second data rate or bit rate and bit error rate of 10 of negative 10. Yeah, this is your bit error rate. Bit error rate, yeah, 10 of negative 10. Okay, so the components proposed for this link are given as below. So these are the components proposed. So based on these given components, yeah, determine their suitability. Yeah, so you have to check whether the component used are suitable to be used, suitable to be applied, and then calculate what should be the SNR of the link. Yeah, signal to noise ratio of the link. If the load resistors RL is 5.3 kilometers, 5.3 kilo ohm, yeah. The RL is 5.3 kilo ohm and the absolute temperature T is 300 Kelvin. Okay, so the component used in our system is the LED, the source is LED of this wavelength 820 nanometer gallium aluminum arsenide, which couples a power of 12 microwatt into a 550 micrometer fiber, which is a multi-mode. Okay, and the rise time is 11 nanoseconds, so the T source is 11 nanoseconds. Okay, for the fiber, we have 50 micrometer core, which is the multi-mode fiber. NA, numerical aperture is 0.24. The attenuation is 5 dB per kilometer. Yeah, that should be your attenuation, the alpha. The dispersion is 1 milliseconds per kilometer, and 4 connectors with 1 dB connectors. Yeah. Okay. While for the detectors, yeah, this is alpha, yeah, attenuation. The dispersion is 1 milliseconds per kilometer, and the connector loss 4 connectors with each connector loss is 1 dB. Yeah. While for the detector, we have a fin photodiode where the responsivity, this is responsivity. We have seen, we have understood what is responsivity in chapter 5 before, on responsivity. The CJ is 1.5 picofarad. The capacitance of your photodiode is 1.5 picofarad. The dark current, dark current ID is 10 picoampere. The rise time of your photodiode is 3.5 nanoseconds. So it means that your T detector is 3.5 nanoseconds. And the minimum mean optical power is negative 86 dBm. So this is the receive power of your pin photodiode. Yeah. Okay, so basically these are the component used. So we have to check their suitability, whether it's compatible with the proposed NRZ digital link with a 30 megabit per second bit rate. Okay, yeah. Right, so if we base on these given components, we notice that both rise time and also gain or losses for the components are given, right? So in order for us to check their suitability, we have to use both methods as what we have seen in previous example, where we have to adopt the rise time budget, and also we have to adopt the power budget analysis, to show whether the system, the components is suitable to be used. Okay, so let us proceed with the system, based on the rise time budget analysis. So before that, let us calculate the what we call this, the rise time, rise time based on the 30 megabit per second bit rate. Okay, so we have that the rise time based on a given system bit rate will be 0.7 divided by 30 megabit, so which is 30 times 10 power of 6. So what should be the value for this? Okay, what should be the value for that? So if we proceed for that, we're going to get the answer for this. The rise time value will be 23 nanosecond. So that should be the maximum. The maximum allowable rise time. Okay, so it means that your calculated rise time shall be not more, or shall be smaller. Shall be smaller than this 23 nanoseconds. So for this, let us calculate the total rise time for the component. We're going to have square root of your source rise time will be 11 nanoseconds. So 11 nanoseconds squared plus the rise time due to the fiber. So we have 1 nanosecond per kilometer dispersion. So since it is 10 kilometers, so 10 times 1, it should be 10 nanosecond. I can just write 1 times 10. So this is the dispersion in total, plus the detector rise time, which is 3.5 nano squared. So end up, we're going to get that the total rise time for the components will be equals to 15.27 nanoseconds. So basically, your calculated rise time is very much smaller as compared to the rise time, or if we are using the 30 megabit per second. So which means that this component can be applied in our system design by applying the rise time budget or bandwidth budget analysis. So the 30 megabit per second bit rate can be supported by these components. Okay, so that should be the first method, which is based on the rise time budget analysis. So I can just note here that this 15.27 is smaller than 23 nanoseconds. So I can just put note that this is okay. So it's understood, Okay, next one, let us proceed with the power budget analysis. Okay, so for the power budget, you have the equation where we have the PTX, the PTX minus the PRX shall be then equals to the channel loss. Channel loss. So end up, you're going to have that the PTX, which is Okay, so if based on the previous question, the PTX is given to be in 12 microwatt. So you have to convert this into a dBm unit, yeah, into the dBm unit. So by having a, let me see, so we're going to have a, we call that 12 microwatt, yeah. So 12 microwatt, so we have a 10 log of 12 microwatt divided by 1 milliwatt. Okay, so for this, you're going to get your power in dBm. Okay, and that should be equals to negative 19.2 dBm, yeah. So that should be your power, yeah, the power transmit by the laser source, by the LED, yeah, which produce a 12 microwatt like source power, yeah. So the PTX will be negative 19.2 dBm, okay, and minus your PRX, okay, minus your PRX. So then to put this as MA, yeah, MA stands for system. I forgot about the MA just now. So the PRX, the minimum mean optical power is negative 86 dBm, yeah. So I need to put here that, sorry for this. Okay then. So we have this as a negative 86 dBm equals to channel loss. So channel loss comprised of few components. Okay, so we have a contribution from the connectors and contribution from your fiber attenuation itself. Yeah, so we can write this as equals to, let me proceed here again, channel loss is equals to 5 dB per kilometer multiply with a 10 kilometers length of the fiber. It's 10 kilometers, yeah. So 5 times 10 kilometers, that should be the total attenuation, plus 4 connectors multiply with 1 dB loss for each connectors, yeah, and plus the system margin. That should be the case, yeah. So when we calculate this, the system margin shall be equals to, this will be 86 minus 19.2, okay, and that should be minus 50 minus 54. So what should be the value then? So it should be 86 minus 19.2 minus 54, and up it should be equals to 12.8 dB. So basically from here, we have calculated that the system margin is positive. Yeah, so positive system margin means that the components can work properly. Yeah, the components can work properly because we have a positive system margin. Okay, so that should be, it shows that by using two methods here, the first one is by using the rise time budget, and second one by using the power budget, it shows that components used or the components selected can support or can ensure the functionality of the of this optical system. Yeah. Okay, so this should be the case. The second one is to calculate the SNR. Yeah, is to calculate the signal to noise ratio. Okay, so for this particular case, these are things that we need to understand, yeah, from what we have learned in previous chapter of noise in optical receivers. Yeah, so as what we have learned for that particular chapters, we have learned about the calculation of signal to noise ratio. Yeah, if I can write this for you. Before that, I need to erase this. To erase this part. Sorry for that. Yeah, because I need to have more spacing. Okay then. So let us proceed with the calculation of signal to noise ratio. So if we can recall back from chapter 6 previously, the SNR can be calculated by these equations here, which is equals to the received current, IP squared, divided by the contribution of noise. So for this particular case, since you are having the pin photodiode, so it should be contribution from the short noise, IS squared, and contribution from the thermal noise, which is IT squared. Okay, so that should be the equation that enables to calculate the signal to noise ratio, in which, if we can recall from the short noise current calculation, it is based on 2 times E stands for the charge amount, times the bandwidth B multiplied with the IP, the received power, plus the duct current value. So the received current and the duct current. So this is the equation that enables to calculate the short noise, whereas for the IT, the thermal noise, this is to be based on the equation of 4K TB divided by the RL, where K stands for the Boltzmann constant, T stands for the absolute temperature, B stands for the bandwidth, while RL stands for the load resistors. Yeah. Okay. And the bandwidth, because we based on this equation, both thermal noise and short noise do relate, do need the values of the bandwidth. So the bandwidth can be calculated based on what we have seen previously, 1 over 2 pi of RC. Okay, so we have R given the questions. If we can recall back, R is equals to 5.3 kilometers load resistors, whereas the capacitance is 1.5 picofarad. Okay, so we can have that the R is 5.3 kilo. Okay, whereas the capacitance C is equals to 1.5 picofarad, or times 10 of negative 12. So that should be the bandwidth of your receivers, and for this, it's going to have the value of 20 megahertz. Yeah? You can prove this on your own, yeah, 20 megahertz. Okay, so this B shall be now applied into these equations of a short noise current and the thermal noise current. Okay, K is a Boltzmann constant. You can refer to chapter 6. Yeah, T is given to be 300 Kelvin. RL is given. Okay, IP is to be calculated. ID is given. ID is equals to 10 picoampere. You can base on the question just now. Yeah, given here that the ID duct current is 10 picoampere. So it shall be used here in calculating the short noise. Okay, how to calculate the IP then? That's question, yeah, because IP shall be used in calculating the SNR. So IP is the received power, and the received current, my apologies, received current, and this should be based on the responsivity values, yeah. So based on the what we have learned in chapter 5 and 6 just now, previously, yeah, responsivity R of the fiber photodiode will be equals to the received current, the produced current divided by the received power, or the incident current, the incident power, which is P incident. Yeah, that's how we calculate the responsivity. The produced current, yeah, the produced current divided by the incident power. Okay, responsivity is the ability of the photodiode to produce current when triggered, yeah, when we have the incident power of P in. So that's what we meant by the responsivity, ability of the photodiode to produce current. Okay, so this P in basically can be calculated based on the previous power budget analysis. If it can be based on the previous equation. Okay, so the P in, if you base on the equation of power budget, yeah, the PTX minus the PRX shall be equal to channel loss. Okay, so the PTX just now, if you can recall back, it is equals to negative 19.2 dBm. Okay, so we have negative PRX, the received power. Channel loss consists of, let me refer back to the previous slide. It is 5 dB per kilometer, 10 kilometer length, and the loss of 4 connectors. So basically, we have the channel loss value will be 5 dB per kilometer times 10 of length, plus 4 connectors times 1 dB. So that should be equals to 54. So negative 19.2 minus 54 shall be equals to the PRX. So basically, your received power shall be equals to negative 19.2 minus minus 54. So that should be equals to negative 73.2 dB. Okay, so that should be your received power, yeah? And that should be now substituted as a P in, which is negative 73.2 dB. And we need to, sorry, dBm, I apologize. PRX should be in dBm, sorry for that, should be in dBm, yeah? So for this, you have to use a conversion to get the power in watt. Yeah, to get the power in watt. So negative 73.2 dBm, which is the received power that has been calculated before. We have calculated it to be negative 73.2 dBm. So by converting this to a watt, so we are going to get that the P in, yeah, for the negative 73.2 dBm shall be equals to 47.86 picowatt. Okay, so from here, we can have that the IP, which is the produced current or generated current by the photodiode, shall be equals to R, which is responsivity given as 0.38 ampere per watt, multiplied by this incident power, which is 47.86 picowatt, and end up you're going to get that the generated current will be 18.18 picoampere. That should be the IP that shall be used in this calculation of signal to noise ratio. Yeah. So I believe that by this calculated IP, yeah, we managed to calculate the generated current by the photodiode, and when we substitute this into the equations here, you are going to get that your signal to noise ratio, yeah, shall be now equals to negative 5.29 times 10 of negative 6. So yeah, negative 5.29 times 10 of negative 6, and in dB it should be equals to negative 52.76 dB. Okay, so that should be your signal to noise ratio for the given system at the receiver side. Okay then, so I hope that by this you have now understand how to calculate the signal to noise ratio, yeah, in which you need to use the information that we have learned previously in chapter 6, and all of these information shall be very useful, which include the generated current by the photodetector, the dark current, the bandwidth, and all of these parameters, yeah, the absolute temperature, and includes the load resistance. So that will be very useful, yeah, in calculating your signal to noise ratio. Yeah. Okay then. So I think that's all for our syllabus for this semester for the optical comm. Okay. So hopefully you have gained very useful information, very useful knowledge in optical fiber communication, which can be used further in case you have a chance to work in this related field later on. Yeah. Okay, so before I end the class, there are few informations that need to be shared together. Sorry, yeah. Okay, I need to stop recording now.